Download this code from codegive.com, link in the description below. OK, let's dive deep into using Linux BPF, specifically XDP, to drop packets, along with a practical demo and code example. I'll break this down into understandable chunks, covering the concepts, setup, code, deployment, and testing. Understanding BPF and XDP. Before we jump into code, it's crucial to grasp the underlying technology. BPF, Berkeley packet filter, originally designed as a packet filtering mechanism, think dump. BPF has evolved into a powerful, generic in-kernel virtual machine. It allows you to run custom code in the kernel space in a safe and controlled manner. This code can access kernel data structures and can be used for various tasks like network monitoring, security, and performance analysis. The ebpf, extended BPF, is the modern version of BPF, with increased capabilities. XDP, Express Data Path. XDP is a BPF-based technology that provides a way to process network packets very early in the network stack, right after the network interface receives them. This proximity to the hardware gives XDP tremendous performance benefits. Because it operates so early, XDP is especially well suited for high-performance packet filtering, dropping unwanted traffic, and offloading certain network functions. How XDP works. When a packet arrives at the network interface, the network driver invokes the XDP program, if one is attached. The XDP program runs and returns an action code that determines what happens to the packet. XDP_pass, let the packet continue through the regular network stack. XDP_drop, drop the packet. XDP_tx, transmit the packet back out the same interface. XDP_redirect, redirect the packet to another interface. XDP_aborted, abort processing, and generate an error event. XDP_pass is like a standard bridge. XDP_drop is like the firewall that is implemented at the network level. Why use XDP for packet dropping? Performance. XDP can achieve significantly higher packet processing rates than traditional methods, like ibtables, that operate later in the network stack. Efficiency. By dropping unwanted packets early, you save valuable CPU cycles and memory that would otherwise be wasted processing those packets. Programmability. BPF provides a flexible way to define custom packet filtering logic. 2. Setting up your environment. 1. Linux kernel requirements. You need a relatively recent Linux kernel that supports BPF and XDP. Kernels 4.8 and later have good XDP support. Kernels 5.x and 6.x are even better. Check kernel version using uname. 2. Required tools. Clang and LLVM. These are compilers used to compile your BPF code. libf. A library that provides helper functions for loading, managing, and interacting with BPF programs. iprout. 2. Tools for configuring networking. You'll use IP to attach your XDP program to a network interface. Make. A build automation tool. Installation, Debian/Ubuntu. Installation, Fedora/CentOS/RHEL. Installation, Arch Linux. 3. Network interface. Identify the network interface you want to attach your XDP program to, example eth0, in0s3, :0. Use IP link show to list your network interfaces. 4. BPF skeleton generator. Ftool, a command line utility that you can compile into binary. You will need this to load BPF programs. You can download the source code from https://github.com/libbpf/bpf tool. 3. Writing the XDP program, C. Let's create a simple XDP program that drops all incoming packets. Asterisk include directives asterisk. Asterisk Linux/bpf.h, defines BPF related data structures and constants. Asterisk bpf_helpers.h, provides helper functions for BPF programs, example functions for printing to the kernel log. Asterisk Linux/if_ether.h, defines Ethernet protocol constants, example eth_p_ip for IPv4 packets. Asterisk sec, xdp, asterisk this macro tells the compiler to place the xdp_drop function in the xdp section of the elf object file. The BPF loader uses the section information to identify the XDP program. Asterisk xdp_md struct asterisk this structure represents the metadata of the packet. It contains information about the packet's memory location, length, and other relevant data. Asterisk xdp_drop asterisk this is the action code that tells the XDP framework to drop the packet. *license BPF programs must be licensed under GPL compatible licenses. This ensures that the code can be used and distributed freely. 4. Compiling the XDP program. Use Clang to compile your C code into an object file. *02, optimization level, level 2. *target BPF, specifies the BPF target architecture. *d_target_arch_x86_64, defines the target architecture as x86/64. Adjust this if you're on a different architecture, example d_target_arch_arm64. *c, compile only, don't link. *oxdp_drop.o, output file name. V loading and attaching the XDP program. We'll use cprout2 to load and attach the compiled BPF program to a network interface. 1. Load the BPF program asterisk. Replace your underscore interface with the name of your network interface, example eth0. *objxdp_drop.o, specifies the object file containing the BPF program. *section xdp, specifies the section in the object file that contains the XDP program, as defined by sec, xdp, in the C code. To verify the XDP program is attached asterisk. Look for the XDP line in the output. It should indicate that the XDP program is attached. 3. Optional, show ebpf programs loaded on system. This will show all ebpf programs loaded on your system. 6. Testing the XDP program. Now, let's test if the XDP program is dropping packets. 1. Generate traffic asterisk use a tool like Ping or Hoping3 to generate traffic to your network interface. Replace target_IP with the IP address of the system you are testing on. If the XDP program is working correctly, you should not receive any replies. 2. Monitor traffic with cpdump asterisk use cpdump to confirm that packets are being dropped at the interface level. If the XDP program is working correctly, you should not see any packets being captured by cpdump. 7. Detaching the XDP program. When you're done testing, you can detach the XDP program from the interface. 8. Complete example with BPF skeleton, recommended. Using a BPF skeleton simplifies the loading and unloading of BPF programs and provides more structure. This is a more robust and maintainable approach. 1. Create a BPF skeleton file, .skel.h. This file is generated automatically from your C code and contains the necessary structures and functions for interacting with the BPF program. We will use ebpf tool for generating a skeleton. First, rename xdp_drop.c to xdp_drop.bpf.c and then generate the skeleton. 2. Update the C code, xdp_drop.bpf.c. Note, change the extension of xdp_drop.c to xdp_drop.bpf.c. 3. Create a loader program, xdp_loader.c. This program uses the generated BPF skeleton to load, attach, and detach the XDP program. It sets up signal handlers, SIGINT and SIGTERM, to allow for graceful shutdown. The xdp_drop_bpf_open, xdp_drop_bpf_load, xdp_drop_bpf_attach, and xdp_drop_bpf_destroy. Functions are all generated by ebpf tool. Uses libpf helpers for attaching the XDP programs and also for printing debugging information to the console. 4. Create a makefile ***. This makefile automates the build process. It compiles the C code, generates the BPF skeleton, and links the necessary libraries. 5. Build and run ***. The sudo/xdp_loader command will load and attach the XDP program. You can stop the program using Ctrl+C. It will gracefully detach the XDP program. 6. Testing, same as before. Ping to verify the interface doesn't respond. Dump to verify that packets are being dropped at the interface level. 9. Troubleshooting. Permissions issues. You need sudo to load BPF programs because they run in the kernel. Kernel compatibility. Make sure your kernel is recent enough to support XDP. BPF verification errors. The BPF verifier performs static analysis on your BPF code to ensure it's safe and doesn't crash the kernel. If the verifier rejects your code, you'll get an error message. The verifier can be quite strict. Common causes of verification errors include uninitialized variables, out-of-bounds array accesses, infinite loops, invalid memory access patterns, interface name. Double check that you're using the correct interface name. Loading errors. The error messages generated by IP link or the libpf will usually give you clues about what's going wrong. DMESC. The kernel message buffer, DMESC, is your friend. BPF programs can print debug messages to DMESC. Use BPF_printk, helper to print custom log messages in the BPF code. You can then check logs using sudo dmesc grep xdp. Key considerations and best practices. Complexity. While this example is simple, real-world XDP programs can become complex. Use good coding practices, modularity, and testing. BPF verifier. Always write your BPF code with the verifier in mind. Keep it simple and predictable. Performance testing. Measure the performance impact of your XDP programs. Ensure that they're actually providing the expected benefits. Security. Carefully audit your BPF code to prevent security vulnerabilities. BPF programs run in the kernel, so a vulnerability could have serious consequences. XDP modes. There are different XDP modes: native, offload, generic. Native XDP is the most performant, but not all network drivers support it. Generic XDP is slower but works with most drivers. Offload XDP offloads processing to the network card, if supported. IP-Link tries to use the most efficient mode available. Error handling implement robust error handling in your loader program to deal with potential failures during loading, attaching, or detaching the BPF program. BPF maps BPF maps are a way for BPF programs to store and share data with user space applications. They can be used for various purposes, such as statistics collection, configuration, and control. This tutorial provides a comprehensive guide to using Linux BPF XDP to drop packets. It covers the concepts, setup, code, deployment, testing, and troubleshooting steps. Remember to adapt the code and commands to your specific environment and needs. Good luck.